Welcome back. The two great aspirations of structural engineering are to attain great height and to span long distances. This inherent human inclination to build upward can be seen in the column, the second of the 6 principal types of structural elements we'll be examining in this course. Columns are structural members that carry load primarily in compression, and they've been integral components of the great structures from antiquity all the way to the present day. The column is the most prominent feature in many ancient structures, from Egyptian religious complexes at Karnak to the familiar temples of classical Greece. Indeed, the classical Greek architectural orders, Doric, Ionic, Corinthian, are defined largely in terms of their columns. Note, for example, that the columns in a Doric temple, like the Parthenon, have stocky proportions and simple capitals. The capital, by the way, is the decorative head on the top of each column. The profile of these columns, that is the shape when viewed from the side, also has a very interesting feature. They exhibit entasis, a slight outward bulge in the middle of the column. Entasis is strictly an aesthetic embellishment. It has no structural purpose. The later Ionic order of the Greek architectural style, seen here in the Erechtheion at Athens, is known by its scroll-shaped capitals, but also note that the Ionic column itself is a lot more slender than the Doric column. This aesthetic trend toward ever more slender columns continued into the High Middle Ages, as we see in this beautiful Gothic cathedral. We usually think of the pointed arch as the defining characteristic of Gothic architecture. Yet, note how important the columns are in defining the soaring height and openness of this Gothic nave. Now, with the advent of mass-produced iron at the start of the Industrial Revolution, builders began substituting iron for stone. And the first type of structural element to undergo this substitution was, in fact, the column. The first known iron structural components in a building were cast iron columns used to support a hood over the cooking hearth of a Cistercian monastery in Portugal in 1752. As we've seen, cast iron is quite strong in compression but weak in tension. And since columns carry load primarily in compression, it makes perfect sense that they were the first iron structural components. It's interesting to note that when iron was substituted for stone in 19th century buildings like London's Euston Station, the old Greek classical orders were often retained. And although these iron columns are far more slender than a stone column would have been, their shape and their detailing are still Doric, just like the Parthenon. We'll see this phenomenon many times throughout the course. When a new structural material replaces a well-established one, builders tend to retain the architectural forms that characterize the older material. But over time, column configurations that were more appropriate to the properties of iron did emerge. This development took place almost exclusively in industrial settings, like the British textile mills of the 18th and early 19th centuries. Here, the need for economy and fireproofing stimulated innovation without any particular regard for aesthetics. These innovations in iron structural framing stimulated further efforts to develop optimized iron and steel structural shapes. For example, most people would refer to this as an I-beam, but really it's more accurate to call it an I-shaped section because of its cross-section shape, because it's just as likely to be used as a column as used as a beam. You'll see I-shaped columns and structures ranging from the monumental, like the Empire State Building shown here under construction, to the diminutive, like the famous Farnsworth House designed by Mies van der Rohe in 1951. In more recent years, custom fabricated steel box columns were developed to meet the unique structural demands of tall buildings like the World Trade Center. In this photo, each of those parallel white lines you see soaring up along the side of the building is a structural column. In some modern structures, like the new Beijing Capital International Airport, we see a highly refined column configuration. These columns, the red structural elements you see in front of the building, are hollow steel tubes up to 130 feet tall and over 7 feet in diameter. In a sense, it seems that we've come full circle. These columns, with their circular cross-section and a bit of a bulge, bear an amazing resemblance to the stone columns of ancient Greek temple porticos. But in the Beijing airport columns, the hollow cross-section and the bulging profile serve structural purposes, as we'll see shortly. We normally think of columns as being oriented vertically, but in practice, any structural member that carries load primarily in compression exhibits essentially that same behavior, independent of its orientation. So, for example, in the Chuto Bridge, these diagonal members, which are called end posts, carry load in compression, and therefore they need to be analyzed as columns, even though they happen to be oriented in a diagonal direction. To avoid confusion, engineers sometimes refer to columns more generally or generically as compression members. So with that brief historical overview of columns as background, let's begin our exploration of the scientific principles of column behavior. And what better place to start than the quintessential compression member, Trajan's column in Rome. Trajan's column is one of many examples of grand public works that were commissioned by Roman emperors to glorify the empire and themselves. It was built in the early 2nd century AD to commemorate the Emperor Trajan's successful military campaign against the Dacians. While Trajan's column is most famous for the spiral sculpture that adorns its outer surface, it was also a very significant construction achievement as well. What I'd like to do is to try to build a model of the Trajan's column as a way to sort of illustrate how it came together. That 98-foot shaft was assembled from a series of 19 cylindrical marble drums, each 11 feet in diameter. Those drums were stacked on top of each other, one block at a time, each one weighing about 32 tons. So the process of constructing this structure really was an extraordinary achievement in construction engineering. And that's particularly true because when the column was built, there actually were two major structures already in existence on either side of it, very close by. So here we have the basic column constructed from this stack of cylindrical drums, and all we need to complete our model of Trajan's column is the capital that goes on top. Now, you may remember last lecture, I did a concrete casting as a way of demonstrating the versatility of form of concrete. Here are those forms, and now it's time for us to see how our efforts have paid off. What I'm going to do is remove the wooden formwork that we used as the basis for forming up the shape of the column. And here we do indeed have our casting of the capital of Trajan's column, a pretty good illustration of concrete's versatility of form, and a wonderful opportunity for us to complete our representation of Trajan's column, surmounted by an appropriate capital. So how does Trajan's column work as a structure? Let's begin our analysis with external forces, and then we'll calculate the associated internal force and stress. As this free body diagram shows, the principal load acting on the column is its own weight. And weight is just volume times the density of the material. The maximum internal force, F, as shown on the free body diagram, occurs at the base of the column because the full weight of the column lies above this cross-section and is pressing down on it. Principle of equilibrium shows us that the internal force F must be exactly equal to the weight of the column. And so now we can calculate the actual stress in that column. And here's how it works. Stress is just equal to internal force over area. The internal force is equal to the weight, so we substitute weight for force. But we can represent the weight as volume times density, or cross-sectional area times height times density. And when we substitute that value into the equation, you'll notice that now we have the area term both in the numerator and denominator. We can cancel those out, which leaves us with a very interesting expression that stress is equal simply to height times density. Well, we can figure that out quite easily. The height of Trajan's column, not including the pedestal, is 112 feet, and the density of marble is about 160 pounds per cubic foot. So based on those numbers, we can calculate the approximate stress at the base of Trajan's column at 18,000 pounds per square foot, and doing the unit conversion, that turns out to be 124 pounds per square inch. Now we can evaluate structural performance in Trajan's column by comparing this stress against the strength of the material. A convenient way to make this comparison is to use a measure called the factor of safety, which is very commonly used by engineers both in analysis and in design. The factor of safety is simply defined as the strength divided by the actual stress. If the factor of safety works out to be less than 1, that means the member will fail. If it's larger than 1, then there's some margin of additional safety built into the structure to account for uncertainties like defects in the materials, construction errors, or unanticipated overloads. Well, the strength of marble is about 6,000 psi, and the actual stress that we've already calculated in the column is 124 psi. So the factor of safety is 6,000 over 124, works out to be 48. That's pretty safe. This means that Trajan's column is 48 times stronger than it really needs to be to carry its own weight without having the stone fail in compression. No wonder this structure has stood for nearly 2,000 years. Now, it's important to recognize that this analysis was based on material failure as the basis for evaluating structural performance. There is another potential failure mode that we need to take into account in the analysis of a compression member. To explore this issue, let's try asking a different kind of question about Trajan's column. Instead of looking at the stress in the existing column, let's ask, how much taller would this column have to be before it's so heavy that the stone at its base crushes in compression? That is, how tall would it have to be before the material at the base undergoes material failure? Well, here's the answer to that question. Using the same density and compressive strength from our previous solutions, but now solving the equation in terms of the column's height instead of the stress, we get an amazing result. A stone column would need to be over a mile high before its own weight would cause the stone at its base to fail in compression. It's really astonishing. Let's give it a try. Let's see if we can't replicate this analytical result with our model column. Let's take the capital off, and let's just keep adding pieces to Trajan's column until it gets to be a mile high, okay? So this may take a while, but please be patient. I'm sure it'll be worth our while when we finally get a mile-high column and we have an opportunity to see it fail. Well, clearly we're not going to get to be a mile high. And I think you can already see that long before this column gets to be a mile high, something else is going to happen, something bad. As the weight continues to pile up on the top of the column, at some point we're going to start seeing instability occurring in the column rather than a material failure. And notice the base of the column is completely intact. There was no material failure. Instead, we saw a different kind of failure mode. It was not a material failure, but rather a stability failure, which we call buckling. Now, buckling is a failure mode that occurs when a member, and in this case, I'm going to demonstrate it using a member that will buckle in a slightly more controlled mode, when a member is subjected to a gradually increasing axial compressive load. And even though the load is purely axial, at some point, the column suddenly deflects laterally. And that deflection is often quite catastrophic. It's important to recognize that even though a buckling column deflects laterally, the load that I am applying is purely axial, like this. The lateral deflection doesn't occur because the column is initially crooked or because the axial load is slightly off center. Yes, these conditions would certainly cause the column to buckle at a slightly lower load, but they don't cause buckling. If we could somehow build a perfectly straight column and apply a perfect axial load, buckling would still happen. We owe our understanding of buckling to the genius of one man, the great Swiss mathematician Leonhard Euler. Euler was one of the most accomplished intellects of the 18th century. He made enormous contributions to our knowledge of calculus, trigonometry, optics, astronomy, mechanics, other aspects of math and sciences. But to engineers like me, he's venerated as the guy who unlocked the secrets of column buckling. Euler developed a scientifically based mathematical model to predict the axial force at which a column will buckle. That model is known even to this day as the Euler buckling equation. And here it is. The basic idea here is that the force at which a column buckles depends on, first, the modulus of elasticity, a measure of the material's stiffness, times the area moment of inertia, a measure of the cross-section's resistance to bending, divided by the column's length squared, and then finally the remaining term pi is just the number, 3.14159 ... So the only term in this equation that you haven't actually seen previously is this area moment of inertia. It's a geometric property of the column's cross-section, calculated from standard formulas. For example, the moment of inertia for a rectangular cross-section is just 1/12 times the width of the rectangle times the height cubed. Now, rather than doing calculations, let's try to understand the Euler-Buckling equation by comparing the behavior of several different real-world model columns. We'll do 3 different comparisons, and in each case, I'll change just one physical property, first the material, then the cross-section, and then the length, and we'll examine the effect of each change on the column's buckling strength as a result. So let's give it a try. Start with this pair of columns. They are identical in size. They're both 3 feet long, and they have a cross-section measuring 3/8 of an inch on each side. But this one's made of wood, while this one is made of steel. So which one do you think will be stronger in buckling? I hope you said steel. The critical buckling load for the steel column turns out to be 364 pounds. For the wooden one, it's only 20 pounds. And indeed, if I apply a load to the top of this column, it does indeed buckle relatively easily. And you can't tell, but I'm here to tell you, based on my perfectly calibrated arm muscles, I can tell you that this is almost exactly 20 pounds, causing the column to buckle. When I try to do the same thing with a steel, I can't make it budge. There's no way that I'm going to be able to buckle this column by hand. Now, when I asked you which column is stronger in buckling, you instinctively said steel. And you were right. But if I asked you why the steel column is stronger, some of you might have answered, well, because the steel is the stronger material. And if you did, you'd be incorrect. It's not because steel is stronger in compression that it's stronger in buckling, but rather because it is a stiffer material than wood. This slide shows you my calculations for the 2 columns. And you can see that the only number that changes between those 2 calculations is the modulus of elasticity, the slope of the elastic portion of the stress-strain curve, a measure of stiffness. It's the stiffness of the material that affects buckling. The strength does not. Let's try another of these buckling comparisons. And this time, we'll test 3 different columns. All 3 are made of wood, and all 3 are the same length. When I built these 3 columns, I used exactly the same amount of wood, but 3 very different cross-section shapes, as shown on this slide. The first one is the 3/8 inch square cross-section that we just used in our previous demonstration. The second is a flat 1/8 inch by 1 1/8 inch member. And the third is a hollow tube. It's about 7/8 inch square, and the wall thickness is less than 1/16 of an inch. Notice that all 3 cross-sectional areas are exactly equal. They work out to be 0.14 square inches. But the moments of inertia are quite different. Because the moment of inertia is a measure of the cross-section's resistance to bending, it's greatly affected by the distribution of material with respect to the member's axis. If much of the material is placed far away from the axis, then the member resists bending effectively, and therefore the moment of inertia is high. If all of the material is concentrated very close to the axis of the member, then the resistance to bending is very poor and the moment of inertia is low. Thus, this flat plate has by far the lowest moment of inertia because all of this material is concentrated very close to the axis of the member. The hollow tube, on the other hand, has a very high moment of inertia, at least relatively speaking, because most of the material is placed far away from the axis of the member. And of course, that solid square section falls between those 2 extremes. So based on these numbers, what's your prediction about the buckling strengths of these 3 columns? The moment of inertia is in the numerator of the Euler-Buckling equation, don't forget. So the larger moment of inertia should result in the larger value of P critical. That's the larger Euler-Buckling load or force. We've already seen that this column buckles at a load of 20 pounds. This is the 3/8 inch square column, the one in the middle of this range of moments of inertia. And now let's try this flat plate. The Euler buckling equation tells us that this ought to buckle at a load of about 2 pounds, and indeed, it buckles at an extremely low level of load. Just a slight push causes it to kick out sideways. On the other hand, the calculated Euler buckling load for the hollow square section works out to be 200 pounds. And again, there's no way that I can actually buckle it by hand. Remember that all three of those columns used exactly the same amount of material. And so that wide range in their buckling strengths is a clear illustration of the benefits that we get from using a cross-section with a large moment of inertia. Finally, we want to investigate the effect of length on buckling strength. So once again, let's return to the demonstration table. And this time, I'm going to once again start with my baseline column. That's the 3/8 inch square member. But this time, I'm going to compare it against another wooden column with exactly the same cross-section. Both of them are square, same size. But now, obviously, this one is significantly shorter. It's only 6 inches long. Predictions, please. Which one of these two will be stronger in buckling? What do you think? Well, clearly it's going to be the shorter one. And in fact, its calculated buckling strength, according to the Euler buckling equation, is 800 pounds. There is simply no way I'm going to be able to physically cause this column to buckle myself. I've got to take it into the lab and crush it in one of our testing machines. The difference is so drastic because the column length is squared in the denominator of the Euler buckling equation. The length of that short column is 6 times smaller than the length of the longer column, and so the corresponding buckling load is 6 squared, or 36 times larger. Now, we really could load this column up to 800 pounds in order to cause it to buckle, but could we really get all the way up to 800 pounds before it failed? Isn't there some point at which the wood material itself would fail? Isn't there some point at which, when we apply enough pressure to this material, it would just physically crush in compression? Well, yes, in fact, there is. For any column, we always must consider 2 different possible failure modes, buckling and material failure. Thus far in our series of comparisons, we've only been considering buckling. Now we have to talk about material failure, and this is how we determine the material failure load. We start with our basic definition of stress, force divided by area. At failure, we know that strength is exactly equal to the stress. That's what material failure is defined as. Therefore, the strength at failure is equal to the failure force divided by the area, and we can just algebraically rearrange that equation in terms of failure force, and it turns out that the failure force can be calculated as the strength times the area. Remember that the area of all 4 of our wooden test specimens was exactly the same, so we can substitute that area in, do the calculation, and find out that the material failure load for all of those columns is exactly the same, 773 pounds. So now think about it. Think about those relative values of buckling strength versus material failure strength. For 3 of the 4 test columns, the critical buckling load was lower than the material failure load. So if I put these 3 columns in a testing machine and gradually increase the load from 0 to failure, buckling would be the controlling failure mode because buckling would always occur before the material failure load was reached. In the 4th case, the short column, the material failure load of 773 pounds is less than the critical buckling load of 800 pounds. So the strength of this column is controlled by material failure, not buckling. If I load this short column to failure like this, the material will crush in compression before it fails in buckling. And if I shorten this column any further, say from 6 inches down to 3 inches, I'd get no additional increase in strength because the material failure load doesn't depend on the length of the member. So in summary, Leonhard Euler's wonderful equation tells us that we can increase the buckling strength of a column in 3 ways. By using a stiffer material, like steel, by using a cross-section with a larger moment of inertia, like a hollow tube, or by keeping the length relatively short. Of these 3, length has the greatest influence because it's squared in the denominator of the equation. Now let's see how we can apply our newfound knowledge of buckling to better understand real-world structures. I mentioned this real-world structure briefly in Lecture 4. It's a diminutive but historically important storage building located at Watervliet Arsenal in upstate New York. It is the oldest all-iron structure in the U.S., built in 1859 by a guy named Daniel Badger, who was one of America's pioneers in iron building construction. I love this building. I love it as an example not only of a historically important early American structure, but also because the interior structure, shown here, is completely visible and it's beautifully configured to communicate how it carries load. And here's an even better view of that internal structure for our purposes, because we want to look at both the roof trusses, where we'll find some compression members, and at the main columns, which are visible on the right-hand side of this photo. For now, recalling that a truss is composed entirely of members that carry load either in compression or tension, can you identify any of the compression members in this truss based solely on their shape? Take a hard look. If you chose these two, you're absolutely correct. Based on the experiments we did earlier, it should be clear that these other members, the slender rods down below and these diagonals, must be tension members. They can't possibly be in compression because they're so thin. They'd buckle at a tiny level of load. But the two heavy struts were clearly designed to resist compression. As we saw earlier, hollow tubes would be the optimum shape for resisting compression. The problem is, it's very difficult to use a hollow tube in a truss because tubes would have been very difficult to interconnect with the other members that form this triangular framework. So Badger did the next best thing. At least the next best thing with respect to the technology that was available at the time. He used cruciform or cross-shaped members like this, using this specific cross-section dimension. The shape that Badger chose for these compression members does in fact increase the moment of inertia by about 35% in comparison with a solid square cross-section using the same amount of iron. And though you can't tell it from this picture, these cruciform members are actually made of cast iron, which was certainly the right choice for a compression member, while the rest of the truss is wrought iron. Clearly, Daniel Badger knew what he was doing. Note that, viewed in profile, these members have a slight bulge, similar to the modern columns that we saw in the Beijing International Airport. What's going on here? Well, it turns out that structurally, that bulge makes perfect sense, because a buckled column bends more in the center than it does out near the ends. And since it bends more in the center, it has greater need of resistance to bending out near the center than it does at the ends. So it makes perfect sense to make the column thicker in the middle than it is out near the points of support. Effectively, what Badger and the designers of the Beijing Capital International Airport knew was that you should give the column the most resistance to buckling at the point where it's most needed. Now let's look at the columns in the Watervliet Arsenal building. The interior columns of the Watervliet building are hollow cast iron pipes, 8 to 10 inches in diameter, with a total length of 29 feet. Now, that hollow circular cross-section is clearly a very appropriate choice for resisting buckling. Nonetheless, this is an extremely slender column, or at least it appears to be, and therefore it appears to be quite susceptible to buckling. But wait! This column is actually much stronger than it appears. When a slender compression member like this one, and like the Watervliet Arsenal column, is supported only at its top and its bottom, when it's loaded to failure, it buckles in a single curve. Notice the shape of the single curve. But the Watervliet Arsenal building has this second floor gallery located right here. And if you look closely, you'll see that the column itself is physically attached to that second floor gallery, which then has the effect of adding a point of lateral bracing to the column. As a result, if we really loaded this column to failure, we would see that it buckles not in a single curve, but rather in a double curve or S shape like this. And you might also have noticed that in order to buckle the column in its original configuration, it took very little load at all. In this configuration, I have to pull considerably harder to get it to buckle, which tells me that somehow the addition of this point of lateral bracing has significantly increased the buckling strength of the column. The reason it did was because the addition of the lateral bracing effectively changed the length of the column from the full height of 29 feet to the height from the top down to the level of the bracing point at that first floor gallery. We call this the effective length of the column, and as we've already seen, reducing the length of a column can significantly increase its buckling strength because the length is squared in the denominator of the Euler buckling equation. In the case of the specific geometry of the Watervliet Arsenal building, the addition of that lateral bracing point at the first floor gallery had the effect of increasing the buckling strength by about 250%. In general, the strength of a column is determined by the length between points of lateral support, which in many cases can be considerably shorter than the overall length of the column. It's clear that Daniel Badger understood this, and he took full advantage of it in his design of the Watervliet building. Sometimes the role of lateral bracing in the strength of columns is decisive, as we'll discuss in Lecture 19 when we examine the tragic collapse of the World Trade Center on 9/11. In today's lecture, we've learned the basic concepts of compression and buckling, and we've seen how columns evolved from antiquity to the present, opening the door to structures of greater scale and complexity. In ancient structures, stone columns were proportioned primarily for appearance, not efficiency, and thus were invariably much stronger than they needed to be. But with the advent of iron construction, columns with slender proportions became both possible because of the material's greater strength and necessary because of the need to minimize cost. Slender columns are susceptible to buckling, and so they couldn't be incorporated safely into structural systems until engineers were equipped with analytical tools capable of predicting buckling failure. The great Leonhard Euler provided this tool for us, and armed with the Euler buckling equation, engineers developed compression members with new cross-sections and new profiles, and structural configurations with new bracing arrangements. These innovations altered how we think about columns and greatly improved efficiency while opening the door to new varieties of great structure. The two great aspirations of structural engineering are to attain great height and to span long distances. In this lecture, we've seen the inherent human inclination to build up as reflected in the column. Next lecture, we'll see the inherent human need to build across, manifested in the beam. Until then, thank you.